My guest today is Dr. Geoffrey Ellis, who is a petroleum geochemist with the Energy Resources Program of the US Geological Survey. His research interests encompass the areas of organic and inorganic interactions in petroleum systems, gas isotope geochemistry, and the controls on sedimentary organic geochemistry in aquatic environments. Welcome, Jeff.
Oh, thanks for having me, Gil.
Yeah, so I want to start with I think this was a paper or a talk. It's entitled Hidden Hydrogen. Does Earth hold vast stores of a renewable carbon free fuel? So to set the context here, so you say here the Malian discovery was vivid evidence for what a small group of scientists studying hints from seeps, mines, and abandoned wells had been saying for years. Contrary to conventional wisdom, large stores of natural hydrogen may exist all over the world, like oil and gas, and not in the same places. These researchers say water rock reactions deep within the earth continuously generate hydrogen, which percolates up through the crust and sometimes accumulates in underground traps. So before we get into the details of this, Jeff, so for the general public, so hydrogen is the lightest molecule, I believe. It's one proton and one electron sort of going around it. So it's the simplest possible thing. And it's very light and it is very reactive, I suppose. So when it meets oxygen, it releases a bit of energy and then water forms from it. So that energy is quite useful for us, and there is no waste product coming from it. So hydrogen,
Right.
if it's naturally available, is clearly it's a game changer for humanity in general, right? So do you want to talk more about, sort of hydrogen? And so let me ask you this in a general context. So the hydrogen is the most common molecule in the universe, but the Earth's creation was pretty violent. So my intuition was that, the primordial hydrogen, if any, on Earth would be small, but that is not necessarily the case, right?
That's correct. Yeah. When the Earth first formed, it coalesced out of essentially a cloud of dust that was circulating around the solar nebula, and that solar nebula was composed of about 80% hydrogen, and the rest helium and a few other heavier elements. And so very large quantities of hydrogen certainly were incorporated into the very, very earliest Earth. But as you note, this was a very violent, dynamic time, a lot of molten magma. And you can imagine the planet of just bubbling lava. And so it's thought that the vast majority, possibly all of that early primordial hydrogen was lost to space. But there is a school of thought and some evidence to suggest that there may be some of this primordial hydrogen that actually was dissolved into this magma and got into deeper parts of the Earth and has been preserved over the entirety of Earth's history and is seeping out of the depths of the Earth even as we speak today.
Mm. So do we know the chemistry of so hydrogen sort of seeping into the magma? Do we know the chemistry of it? How could that happen? Yeah.
There's actually experimental studies as well as theoretical calculations about the solubility of hydrogen in molten silicate rocks, and it is soluble. You can dissolve it in that magma. The question is whether, during this sort of violent thermal overturning, and as this magma is circulating around, there's a lot of opportunity for bubbles to form and gases to be released. And as the Earth starts cooling, you form a crust over the top, and then you start to trap some of these volatiles. So the details of when you start trapping volatiles and how much could be in there, that's really the critical question. And there's a lot of uncertainty around that. I mean, an intriguing part to this is that we know that the Earth's core is composed of primarily iron and nickel. But we know from seismic velocities, when we track earthquake motion through the Earth's core, we know that the seismic velocities do not match exactly with a pure 100% iron-nickel mixture. Mm-hmm. And in fact, the core has to be a little bit less dense. There needs to be some lighter elements in the Earth's core. And we don't know what element or elements might be there. It's not a unique solution to that. So it could be some, carbon or nitrogen or sulfur or hydrogen. And there are actually experimental evidence to show that you can make iron-nickel hydrides, where you just have hydrogen attached to the iron and nickel. And you could, in fact, solve this seismic abnormality by just putting hydrogen into the Earth's core. So it could just be a nickel iron hydride core. Oh, wow. And in fact, that would not be, it's actually not stable over long periods of time, so that this nickel iron hydrides would be sublimating and giving off hydrogen gas, and that could be seeping out of the Earth's core. And if that were in fact true, then that would be a huge volume of hydrogen that's coming out of the Earth's core continuously. But there's another important aspect of this is that we know from the thermodynamics of the Earth's mantle. So the Earth has a solid iron nickel core, and then outside of that we have this liquid state mantle that is made up of melted silicate minerals, and the lower mantle under those pressure and temperature conditions, hydrogen is stable. The hydrogen would actually partition between methane, water, and molecular hydrogen, H2. But when you get to the temperature and pressure conditions of the upper mantle, it becomes more oxic, and the molecular hydrogen is actually not stable. And all the hydrogen should partition into methane and water, and there shouldn't be any molecular hydrogen in the upper mantle. But that's assuming that it's all reached thermodynamic equilibrium. And from my decades of studying Earth science, I find that usually the Earth is a lot more complicated than we imagine in these sort of simplistic models. And so I think it's possible that there could be some heterogeneity and some places where you have metastable phases, or you have things where it's not reached equilibrium, and there's possibilities for hydrogen to escape through this upper mantle and get to the crust. And then once it gets into the crust, it could be stable again. There are places where hydrogen then is stable.
Yeah, that would be a very lucky break for humanity if there's a large amounts of hydrogen in there, and it's slowly sort of oozing out, so to speak. Because hydrogen, I understand, is the cleanest fuel that you could imagine in the context of all the environmental issues that we are currently having. And then you talk about this before we get to your other papers. They could be regenerating, the crust or the Earth in general could be regenerating hydrogen in some iron-based reactions or some other reactions, right? So what are those reactions?
Yeah, so in addition to this primordial hydrogen that may be stored deep in the Earth, hydrogen absolutely is generated in the Earth's crust. And in fact, there are dozens of natural processes that are capable of generating hydrogen. But if we're interested in hydrogen as a resource that we could use for energy or as a feedstock for chemicals, then we need a process that could generate large amounts of hydrogen. And most of these natural processes generate relatively small amounts of hydrogen, so they can be neglected. But there are a handful of processes that are known to generate large volumes. And so the one that's most commonly mentioned is the one that you just referred to, where we have oxidation of iron by water. This is essentially the process of forming rust. Yeah. And this is a thermodynamically favorable reaction. It's actually exothermic. And if you have water in contact with iron-rich minerals at the right temperature conditions, you can generate hydrogen. And in fact, the reaction is quite rapid. We can go out to mid-ocean ridges in the oceans and actually see hydrogen being generated in real time. And we can also replicate it in the laboratory. But there's also another process called radiolysis. It's where you have the natural radioactive decay of radiogenic minerals. And if you have water in contact with those minerals, that radiation is capable of splitting water and forming oxygen and hydrogen. And this process is much, much slower than the iron oxidation process. However, we have radiogenic rocks that are very, very old. Some of the oldest rocks on Earth have radiogenic minerals in them. And so over a period of billions of years, if you have water in contact with this rock, you could generate very large amounts of hydrogen. So those are the two that I think have gotten the most attention and are considered most widely to be the mechanisms for generating natural hydrogen.
So the iron rusting and producing hydrogen, does it require energy, or is it natural?
So it requires higher temperatures. Yes, so it does require some energy. So yeah, the reaction is most rapid at around 300 degrees Celsius, and at higher temperatures is actually slower, and as well as lower temperatures it gets slower. But there is evidence that it still does happen even at temperatures below 100 degrees Celsius. It's just a much slower rate of reaction.
But so I'm just from an engineering perspective, it's not practical for us to put iron into water. I'm imagining a large pool of lake, water or something, put a lot of iron in there, and then slightly increase the temperature. It's not practical to generate hydrogen, right?
Well, yeah, that opens up a whole question. There's actually people have proposed that we might, let's back up for a second and say that not all iron can be oxidized to generate hydrogen. And so it has to be in the right form. It has to be reduced iron that you can then oxidize, but also you have to get that iron into an aqueous solution. You have to dissolve it into water. And so to do that, you have to have minerals that the mineralogy of the rock has to be suitable that you can dissolve some of that iron. And then also, once that iron becomes oxidized, you have to then precipitate that iron, take it out of solution, because once you oxidize your iron, this oxidized iron will build up in solution in the water. And if it's not removed, then the reaction will reach equilibrium and the reaction will stop. And so it's some fairly complicated geochemistry that you have to have the right rocks where you can dissolve the minerals and get the iron, but then also precipitate out the products so you can keep the reaction moving forward. But this does touch on an idea that people have suggested that there are a lot of these rocks in the subsurface that do have this potential for generating hydrogen, but not all of them have generated hydrogen. Maybe they weren't hot enough, or maybe there just wasn't water really moving through them to cause this reaction. So it's possible that we could go out to some of these places and actually engineer this, go in and drill and fracture the rocks and then inject water and then start making hydrogen. And so this is something that the US Department of Energy has just recently invested a bunch of money into research programs to see if we could figure out ways to engineer what they call stimulated hydrogen generation.
Stimulated hydrogen, yeah. That's really fascinating. So I want to get some of the numbers, Jeff. So model predictions of global geologic hydrogen resources. So you say here geologic hydrogen could be a low carbon primary energy resource. However, the magnitude of Earth's subsurface endowment has not yet been assessed. Knowledge of the occurrence and behavior of natural hydrogen on Earth has been combined with information from geologic analogs to construct a mass balance model to predict the resource potential. So we sort of talked about two different things here. So it's sort of the stuff that's stored in there, in the mantle, in the subsurface, and then there's stuff that's being produced. If I understand this correctly, the stuff that's being produced is not big enough for us to get excited. What that would imply is that we have to really think about what is already stored in there, right? Is that the way to think about it?
Yeah, that's right. We have fairly good idea of how much is being generated every year in these crustal rocks at places like mid-ocean ridges and other volcanic settings. And the total amount generated is really not that big, especially when you realize that there's no way that we could recover all of this. We're not going to go out to mid-ocean ridges and farm hydrogen or collect it there. That's just really not practical. So yeah, what's being generated annually is probably really not going to constitute a resource. But the Earth is 4.6 billion years old, and these processes have been going on throughout the duration of Earth history. And so if some fraction of that hydrogen got into some porous rocks and got trapped there and was preserved there, then that has a lot of time to form accumulations. And so which is analogous to oil and gas. Petroleum generation takes millions of years. And then those hydrocarbons are generated, and they typically migrate away from the source rock and get trapped into some porous rock and get preserved there. And so we're actually exploring for these accumulations where hydrocarbons have gotten trapped, not where the hydrocarbons are really being generated. And so that's what we're really focusing on, is where natural hydrogen may have accumulated over some period of time.
Yeah, I didn't quite appreciate this. So it's not necessarily primordial hydrogen. I mean, it could be that.
Right.
But since, as you say, the Earth is 4.5 billion years old, if this regenerative processes have been working, it will have produced a tremendous amount of hydrogen. And if it hasn't really escaped, it would have gotten trapped in some traps that we might be able to get to. And so you say here, stochastic model results predict a wide range of values for the potential in-place hydrogen resource, 100 to 1,000 million metric tons, with the most probable value being around 5 million metric tons?
That's right. 5 million
metric tons. So what does that? So I got confused, Jeff. How do we weigh hydrogen? I mean, it's a gas. It's lighter than the general composition of the air. So it's a molecular weight that we are tagging onto.
Well, yeah, as you point out, it is a gas. So if you have, we can talk about the volume of a gas, but of course the volume depends on the temperature and pressure conditions that you're holding it at. And so the mass, it does have mass. It's a very light element, but it actually, each one of those atoms does have some mass to it. And so if you have some volume of hydrogen, it also will have a mass to it. So we often refer to hydrogen in terms of tons of hydrogen, because it avoids the confusion. If I talk about cubic meters of hydrogen, then I have to know what temperature you're talking about and what pressure is it under. And so it gets a little bit more complicated. But for context, currently on the entire planet, we produce about 100 million metric tons per year is how much is used. And
it's actually produced. Actually, we are actually using it.
Yeah, so all the hydrogen that we have today that we use for either for an energy resource or for a chemical feedstock is made, and the vast majority of it is made from fossil fuels. There's two main processes. One is from methane, from natural gas. You can combine methane with steam, water, over a catalyst, and that will then produce hydrogen. But unfortunately, it also produces CO2. And for every 1 kilogram of hydrogen that's produced, you produce about 10 kilograms of CO2. And currently, that's all being vented to the atmosphere. So that's kind of problematic. And so another way we can make hydrogen is actually just by splitting water. But you have to put electricity in to do that. And it takes a fair amount of electricity to do that. But if we want to make clean hydrogen with minimal carbon footprint, then right now what we're relying on is taking renewable electricity from wind and solar and using that to then split water to make hydrogen. But it's currently that technology is really quite expensive right now, and so and we're finding there's some challenges with scaling that up to get to this 100 100 million metric tons or even more. It's proving difficult. We need a lot of minerals, a lot of critical minerals to make all this infrastructure. And there's issues with the intermittency of renewable electricity running these electrolyzers that make the hydrogen have some problems with the efficiency of the methods. So
Yeah, I mean, there is also a question of round trip efficiency, right? So,
yeah.
yeah, um, if you already produce electricity, to put it into something that could produce energy, um, there is transportation questions around it. So there has to be some distinct advantage to hydrogen, either in transportation or remote use or whatever. Because if you already have electricity, you already done it. I mean,
That
there's no
no,
point putting it in the water.
yes, no, you're absolutely right.
Yeah.
But there are a number of sectors where it's really difficult or impossible to electrify. And so, I think one of the big ones is aviation. That from all the conversations I've had with people, it seems pretty clear that we're not going to have battery-powered airplanes that are going to be able to fly across the Atlantic Ocean. And
Yeah.
so we're going to need some sort of other sort of energy source for that. And even if
At
we
least
go
as a
to
backup. At least as a backup, I would imagine, right?
yeah, and right now the focus is really on sustainable aviation fuel, which is using biomass or some other organic feedstock other than fossil fuels. But any kind of sustainable aviation fuel requires hydrogen to make those hydrocarbons. And so we're going to need this low carbon hydrogen for some things like that. Also for a lot of industrial heating processes and so forth. But also hydrogen is a really useful molecule for a lot of things. It's very flexible. And so if we were able to find large amounts of low carbon hydrogen underground that we could simply drill for, I think we would use it in a lot of these places if it was low cost and low carbon.
Totally, yeah, I'm all for it. I mean, if you can find it already existing, it's almost zero cost in the grand, I mean, not zero cost in the grand scheme of things, from an environmental perspective.
Mm-hmm.
It's zero cost. But there are some engineering challenges here. So I remember I had somebody from Australia like 2 years ago, and he from University of Sydney, and he was talking about hydrogen. And I think Australia is very much into this, right? I mean, they seem pretty advanced in their thoughts on hydrogen.
Yeah, yeah. I mean, they are, especially they have a lot of potential for wind and solar, so they're looking very much at producing this green hydrogen from
Green
renewable
hydrogen.
electricity. And I think that they're looking to export it to Asian countries. There's a big market there close by for them.
Mm. So, so suppose I produce electricity in California and I want to ship that electricity. California has negative electricity costs. I just read.
Hmm.
I find this amazing because of all the solar investments we have taken there. So and I want to ship that electricity to Connecticut over the grid. The losses that I would experience in that electric transmission, is it is it smaller or larger than if I were to convert that into hydrogen in California and ship that hydrogen by some sort of transport mechanism?
I've seen an interesting study recently that was comparing the energy efficiency of different fuels and comparing that to the efficiency of transporting electrons across the electrical grid. And the least efficient way to transport energy is actually over the grid.
Oh wow.
And that the most efficient was through oil pipelines. That there's the energy density of crude oil is very, very high, and so you can transport a lot of energy long distance in an oil pipeline. And then natural gas comes after crude oil. And then hydrogen is actually not that bad compared to the transmission lines. But it's not nearly as efficient as crude oil or natural gas.
So we'll be going backwards here, Jeff. So we have excess electricity because of solar and wind, and we're going to convert that into CH4 or some um, something
Right.
like that, and then transport it by trucks to somewhere, and that's more efficient because of all the resistance-based electricity losses. Unless we find, room temperature superconductivity or something
Exactly.
like that. Yeah, yeah.
That's right. Yeah, yeah, that's right.
And so, so your thinking is that so we don't have a very good constraint on how much hydrogen exists on Earth. The range is very, very wide. So if you're trending toward, let's say, two-thirds of that range, you say here that might be enough for, I don't know, 200 years. Um,
Well,
I'm, yeah,
let me clarify that
yeah,
we
yeah,
so yeah we did this model of just trying to estimate how much might actually be trapped in the Earth's crust, and we came out with this number of about maybe 5 million metric tons, plus or minus several million. There's a lot of uncertainty around that, but it's
yeah,
a very, very large number. But there's some really important caveats to that, and so the first one being that this is for the entire Earth's crust.
yeah,
And so most of these accumulations are going to be inaccessible. They're going to be simply much too deep or much too far offshore, or accumulations that are just much too small that they could never economically be recovered.
mm,
So practically speaking, we have to think about how much might even be recoverable, and we think a reasonable number is maybe a few percent of that.
mm,
Most of it, 90, 95+% is just going to be off limits. We're just never going to get to it. But so I did a back of the envelope calculation that if there's really 5 million megatons in the subsurface, and if we could recover 2% of that, that would be 100,000 megatons, a million metric tons,
yeah,
which would be 1,000 years supply of what we're producing today.
yeah,
And it's projected that the demand for clean hydrogen is going to grow up to maybe as much as 500 megatons per year to get to net zero, to make all this aviation fuel and things we would need. So
mm,
that's still 100,000 megatons would give us about 200 years of all the clean hydrogen we need. We wouldn't need to worry about making any green hydrogen or anything else. We could get it all
mm.
just out of the ground potentially if we could figure out where it is and how to get it out of the ground.
Yeah. I mean, it's a dream come true. So for general public, when hydrogen burns, it combines with oxygen and creates water. And this is the cleanest form of burning one could imagine, right?
Mhm.
And so if it releases energy in that process, it's almost, not almost, it is pollution-free energy. So talk a little bit about this Mali discovery. I don't know the name of the town, but I understand that they're actually using naturally occurring hydrogen to power the whole city, right?
Yeah, it's certainly not a city. It's a small village
Yeah.
in the country in Mali. It's a town called Burake Bugu. It's located about 50 kilometers north of the capital Bamako. And it's really a fascinating story where the village had been relying on hand dug water wells for centuries, but they frequently were running out of water. And so they were always struggling to survive on the amount of water they could get. So they, at one point in the 1980s, they got some international aid money and were able to actually drill a well to produce water for the village. And they brought in a company from Italy that had a drilling rig that could drill the well for them. And in the process, they drilled in a few locations and didn't encounter any water. And so they pulled out and moved to different spots. And while they were drilling in one location, one of the villagers noticed that one of the holes that they had earlier drilled, that there was a bunch of gas coming out of this hole. So
Mhm.
they got the drillers and said, "Hey, come check this out." And so one of the
That's
drillers,
dangerous, dangerous gas. Yeah.
well, they didn't realize that it was dangerous gas, and so one of the drillers was leaned over. He happened to be smoking a cigarette and leaned over the hole, and he lit it on fire and blew himself up. But luckily, he was not seriously injured or killed. But it took them weeks to put the fire out and plug the hole, and then they did drill somewhere else, and they found water, and so they made a water well and they left. And then it was 25 years later that an oil and gas company came back to this site, and they knew this story about this flammable gas. So they came back with an oil and gas drilling rig with the intention of producing a natural gas well that they could then use this natural gas. And so they drilled a well and they got the gas, but when they analyzed the gas, they found the composition was almost pure hydrogen, over 98% hydrogen.
Oh, wow.
Which was, it was a big surprise. And so that discovery well was drilled in 2012, and it has been in production ever since. So for more than a decade, they've been producing this pure hydrogen gas. And initially, they brought in a converted internal combustion engine that had been converted to run on hydrogen. And they used that to run a generator to make electricity for this small village. But about a year ago, they actually replaced that engine with a fuel cell, which a fuel cell just combines air with hydrogen and makes water and gives off electricity. And so they wanted to know if the purity of this gas was sufficient that they wouldn't have to do any cleanup. They could just run the gas out of the ground into a fuel cell. And that's been running now for over a year now, and seems to be working well.
99% pure hydrogen. Yeah, so it's a dream come true. So it's so they're making electricity for the village. They're taking care of the energy needs of the village. So do we know if this is regenerated hydrogen, or are they just sort of plugging into what was existing there before?
So most likely this is just an accumulation of gas. There may be a little bit of regeneration. It's a little uncertain, but the well that they've drilled, there is water in the base of the well, and then they're producing from an upper interval where there's a gas cap on top of this water, and the pressure in the well, they've been producing now for over a decade, and the pressure has actually gone up slightly in the well. And so some people have suggested, oh, that means that this is being regenerated and it's generating it faster than they're taking it out. But I think it's more likely that as they're producing the gas, that there's dissolved hydrogen dissolved in the water at the base of the well, and that's just coming out of solution and recharging this gas cap on top of the well. So we don't know. Unfortunately, Mali is a very challenging place to visit these days. The political situation is quite unstable. So not many people have actually been to this site, and there's not a lot of data that's available to know more about this accumulation.
So from what we know, though, so the flow levels are sufficient to continue for about a decade so far, right?
Yeah, but we should be careful to note that this is a very small village, and they're only just have this one well to run this small. So I don't know the number, how many megawatts the generator is, but it's quite small. So this really isn't really a commercial scale type of production that you would think about normally for a gas well.
Okay. So I want to talk a bit about policy, Jeff. So you have a paper here, prospectivity mapping for geological hydrogen. You say here exploration for geologic hydrogen remains in an early stage, and discoveries of high concentrations of subsurface hydrogen are still relatively rare. To facilitate research and exploration for this potential resource, this report presents the first publicly available prospectivity map of geologic hydrogen accumulations in the continental United States. So talk a little bit about, so I know that USGS has this map out on its website, so I don't think we are talking about anything secret. So as we discussed, there are multiple ways hydrogen could be generated, could be already stored from previous processes, could be primordial hydrogen. There are multiple ways that hydrogen could be there on Earth crust. And what you said before is really about the economic question, which is, is it valuable for me to go extract this? How much money do I have to spend extracting it, and how much quantity am I going to get from that process? And so mapping this has huge value for lot of lot of companies and people, right?
Yes, it does have value. I would say it's a very first step in a long process. But essentially, what we did to understand what the potential might be for accumulations of hydrogen to be in the subsurface, we need some kind of a geologic model that would tell us what kind of geologic settings would be most suitable for forming these accumulations. And so to come up with this geologic model, we took a framework that's used in the oil and gas industry, something we call the petroleum system, which identifies a number of geologic features that are needed to come together to form an accumulation of petroleum. And so we took that same framework, but we adapted it for hydrogen. So, for example, the source rocks that generate oil and gas are very different from the source rocks that generate hydrogen, but we need sources for both of them. So we identify what are the source rocks that can generate hydrogen, but then also that hydrogen is very mobile, so it will migrate. And so where are the migration pathways? Where would hydrogen move once it's been generated? And then you need some kind of reservoir rock. You need porosity, space within the subsurface where you could actually build up an accumulation. So what are the good rocks that would have porosity in them? And then you also need some kind of seal, a very impermeous rock that would trap the gas in, so it could be held in place for a long period of time. And so we identified all of these geologic features that need to come together to form an accumulation of natural hydrogen. And then we identified proxy data sets that we could use to map this across the United States. So, for example, this radiolysis of water is one source of hydrogen. So we looked at maps of where the subsurface has radiogenic minerals in it, and we can map out, okay, these are the parts of the U.S. where we would have a good source for radiolysis of water. And then we also have this iron oxidation process. And so where are these iron-rich rocks that could be the source rocks for hydrogen? And then we gave weighting values to each of these input maps, depending on how much we thought this would contribute to an accumulation of hydrogen, as well as accounting for how much uncertainty. There's a lot of unknown about this. And so we actually put a range of values onto all these weightings and then ran a Monte Carlo on that so we could get a distribution of probabilities, and then combine this all together to come up with this net prospectivity that then generate a map to show where are the better places to look. So to be clear, this is not a map that says you should drill here, and that just because this has the highest number on the whole map, that doesn't mean it's the best place. But what it does tell us is that this part of the country is probably a better place to be looking for hydrogen. This other part of the country, maybe not so good. And so, we probably don't need to spend as much time there. But the next step for the companies is then to go to these areas that look interesting and to do more detailed work. You really have to do detailed, more like three-dimensional modeling to really understand what's happening in the subsurface, and then key in on places where you want to actually start drilling and looking for accumulations in the subsurface.
So at least on the surface, it appeared the Midwest is most attractive, especially places like Kansas and Nebraska, right? So
yes,
yeah, go ahead.
Yeah, the middle continent of the U.S. looks quite good. This is because we have the central part of the United States is what we call the part of the North American craton, and that's underlying the rocks at the surface. We have these very old granitic rocks that have a fairly high content of radiogenic minerals and have been in place for more than 1 billion years, and so that's a potentially a good source for natural hydrogen underlying much of the interior of the lower 48 of the U.S. But then on top of that, we have other places where we have what we call suture zones, places where some of the deep crustal material, you have rocks that have been pushed together, and so there's fractures or potential migration pathways for these deep fluids that could be coming up from the mantle. That these also occur in many parts of this interior of the U.S. And then we also have some of these iron-rich rocks that are deposited. One part of the country is known as the Mid-Continent Rift that runs from Kansas up through Iowa and Minnesota and up into Canada and back down into Michigan. And this is an area where well, a long time ago, the North America started to try to pull apart and form a new ocean basin, but then it failed for unknown reasons, and it never really completely pulled apart. But that's an area where you can have some of these iron-rich rocks brought up closer to the surface, and also potential for fluids coming up from much deeper. So all of those elements have sort of come together to make that a good part of the country. But there are other parts of the country that also look very, very attractive.
So when earthquakes happen, could we use that data to get some insights into where hydrogen might be?
Yeah, earthquakes are really interesting because obviously these can be faults that are conduits for fluids coming up from very, very deep sources. But one of the challenges is that it's been frequently observed for many, many decades that actually faults are places where you find elevated concentrations of hydrogen in soils at the near surface. And in fact, when you have seismic activity, very often the concentration of hydrogen goes up along these faults. But
because it's sort of rising from the mantle, or
yeah. So there's a couple of possibilities. One is that when you have fault movement, then oftentimes you get fluids that can move upwards, and so that could be an opportunity for gases from very deep to make their way up towards the surface. But the other possibility is that there's a process called mineral comminution, where you have mineral grains. When you mechanically rub minerals together and grind them, you can actually form radicals. And if you have water present there, those radicals are able to split the water and form hydrogen. So if you just took some quartz sand and you put water in it and you start grinding it very quickly, you can actually generate hydrogen that way. And so almost certainly some of this hydrogen that we see in faults is simply being generated by these rocks grinding against each other with water present there and generating some hydrogen locally. So it's a complicated question.
Yeah, so can we? I'm just speculating. Again, Jeff, I know nothing about. So if you understand what the Earth is doing, could we replicate that in engineering? I mean, could we? All we need is some excess energy to come out. So to grind things, we need to put energy in. But if that's creating enough hydrogen that puts out more energy than what we are putting in, that's a favorable process. So can we do that?
I think with this mineral grinding reaction, I don't think you would get more energy back. But I do think that the engineering of the iron oxidation reaction, that one it could be, if we can find the right places to do it, that one could be really effective. Yeah.
So it's in conclusion, Jeff. So you've been working in this area for a long time. We have a lot of land in the US. Some of it has been explored. We know there is a lot of potential hydrogen, at least in the Midwest, from the map that I saw. What should be sort of the US policy be? I saw an Australian company has gotten leases on some of this land, and they're trying to explore it. So what from a macro policy perspective, you don't have to reveal any secrets. From a macro policy perspective, what should the US do? I mean, if we, as you say, if we have enough hydrogen in there for 200 years, I'm pretty confident in 100 to 200 years we'll get fusion practical,
Right.
and we won't need it anymore. So
Right.
in some sense, it's a bridge mechanism that we can save the Earth with. So it's pretty strategic from that perspective. So what should the US policy be in this context?
So I'm not in a position to speak about policy at all. That's really not what we do here in the USGS. We provide, objective science. But what I can say is that we still need to do a lot more research. There's a lot that we don't understand about this. There's, as we said at the outset, this model of what we think might be in the subsurface has a lot of uncertainty around that. And so we really need to do more research to try and reduce the uncertainty and to help, guide figuring out where the places where we might have, resources in the subsurface. So that's what I really would like to, recommend, is that we continue doing more research in this area.
Put higher constraints on this uncertainty that we have, which is almost like two orders of magnitude, as you say. So what are the research areas that we want to focus on to reduce that uncertainty?
Yeah, so we have this hydrogen system model now that we've developed, which tells us, okay, these are the good source rocks, and these are maybe the good reservoir rocks and seals and so forth. But we don't really understand really all of those elements that go into that are still have quite a bit of uncertainty on them. So for example, what are the best rocks that can really generate hydrogen? As I mentioned, just because there's iron there doesn't mean that it's going to oxidize and form hydrogen. And so the geochemistry of these rocks really has a big role in generating, controlling how much hydrogen can be generated. And so we need to do basic research on understanding what are the good rocks to generate, what's the rate that they can generate at, and then understanding how it moves to the subsurface, and also a key area is how effective some of these rocks are at trapping these fluids. And then also just in the exploration side of things, we have very sophisticated technologies that we now apply in oil and gas exploration. We use seismic data and all kinds of other sophisticated modeling tools and so forth to identify where oil and gas is in the subsurface, so we can go and drill for it. And much of that will be applicable for exploring for geologic hydrogen, but not exactly. There's a lot of ways that it doesn't apply. Oil and gas exploration is restricted to sedimentary basins where we have the source rocks that can generate petroleum. But the hydrogen rocks, the source rocks, are really not those same rocks. These are more typically more what we call crystalline hard rocks. And so the oil and gas exploration tools are not really well suited for exploring in those kind of settings. But those are places where mining companies actually are very actively looking for mineral resources. And they have a whole suite of exploration tools that they use for exploring for mineral resources. But they're looking for the rocks, not for the gases, not for the fluids. And so we can borrow some technologies from mining and some things from oil and gas and recombine them and optimize them to develop the best technologies and strategies for exploring for geologic hydrogen. But that requires a lot of research and some trial and error and so forth.
Yeah, so oil and gas is very interesting. So generally speaking, this is a resource like oil and gas, but it doesn't have the the complications of natural environment complications of oil and gas. And so are oil and gas companies really thinking about this as potential replacement to their products?
Yeah, I would say yes, there's interest. I think that there's a consensus that oil and gas is not going away tomorrow or even, in a decade or two, that we will need and continue to use oil and gas for quite some time. But I do see that the industry sees this as a potential new opportunity for them, and it's something they see that there's a lot of value in this, and so there is quite a bit of interest now in the oil and gas industry in trying to understand what the potential might be.
Excellent. Thanks so much, Jeff, for changing your schedule.
Sure, no problem. No, happy to do it.
Yeah, thanks for spending time with me.
Yeah, you bet.
Bye.
Okay, bye-bye.